chapter on causal models. Hopefully the stuff on statistics and probability and then evaluating statistical hypotheses was clear. We're not going to, from this point forward, really encounter any new math or any new concepts in statistics, really. All that basic stuff of finding the margin of error, finding the relative frequency in the population, and then estimating backwards, finding the relative frequency in the sample, and then estimating backwards to the probability in the population, finding the margin of error, getting those intervals, seeing if they overlap or if they don't, finding the strength of the correlation. All those basic calculations, which really, again, only involve like addition and subtraction. Those are all the things you're going to be using for causal models. The difference will be more in the experimental setup, right? How are these studies designed? And we're going to see 3 different types of studies that you can use to provide support for a causal hypothesis. So up till now, we've talked about finding correlations, right? But I'm sure you all have heard, if you haven't heard, now you've heard, correlation is not causation, right? So what else do we need to show causation? And that's what we're going to be talking about for the next few lectures. Okay, yeah, as I said, we now know the basics, how to evaluate statistical claims about correlations among properties in a population, and we're kind of over the hump with all that sort of mathy stuff, right? It's still in the background, but if you've mastered it, now it's all sort of conceptual. So we'd like to make stronger claims than about mere correlations, right? We would like to know whether high cholesterol actually causes heart attacks, right? Or whether smoking actually causes cancer, not whether it merely correlates with them, right? And the phrase, right? Correlation is not causation. So we need different evidence to prove a causal claim. Why are they not the same? If you need a little convincing, right? For example, using ashtrays is correlated with lung cancer, right? If you've used a lot of ashtrays over the course of your life, you're more likely to have lung cancer, right? Why is that, right? And again, what would that mean statistically? You look at former or current ashtray users, see if there's a higher percentage of lung cancer among them, right, than others. Or sorry, the other way around, right? Is there a higher, given that you have cancer, right? What is the probability that you've used an ashtray? And it's going to be higher, right? Does that mean that using ashtrays causes cancer? Well, obviously not, right? The correlation is that smokers use ashtrays, so smoking correlates with ashtray use, and it's smoking that causes cancer, right? So this is one problem with correlations. There's correlations can be the result of like a common cause, or they can correlate with something that correlates with the cause, right? Red spots are correlated with chicken pox. They're not the cause of the chicken pox. It's the other way around, right? The chicken pox causes the spot. So correlation can be symmetrical, whereas we'll see causation is not. Other examples, there's anthropologists discovered a tribe in the South Seas that believed that having lice promoted good health, right? Because they observed a correlation, right? It wasn't just made up. But it turned out what happened was that lice don't like people that have a fever, right? So it just so happens that if you're healthy, you won't get, if you're sick, you won't get lice, but that doesn't mean that the lice make you be not. Okay, so one difference, as we've just sort of noticed, is that causation is asymmetric, right? Correlation is symmetric. So if A is positively correlated with B, then it follows that B is positively correlated with A. But causation not the same, right? If A causes B, you can't, on that basis, claim that B causes A, right? Now there is sort of reciprocal or cyclical causation. That sort of thing exists. It's not impossible necessarily, but it's certainly not can't be assumed, right? Just on the basis of one direction of causation that you get the other one as well. Um, so why, right? Why is causation asymmetric? Um, that's sort of a deep question for philosophers of science, maybe even right philosophers of time, right? You might think, um, well, time is asymmetric, right? You can't uh, yet we can't really go back in time. We only go forward, right? Various sci-fi scenarios notwithstanding. Uh, so maybe you think that's the source of the fact that there's no backwards causation. There's no backwards traveling in time. Um, maybe, right? But there are correlations that have this temporal asymmetry as well that still aren't causes, right? So your ashtray use will precede you're getting lung cancer, but that alone doesn't make it a cause, right? So just because something is earlier in time, um, that isn't it. So we can't correlation plus temporal asymmetry. That can't really be the whole answer either, right? For what makes something causation. So for the purposes of this course and what they this is what they do in the text, and we kind of just need to stop that conversation. It's an interesting conversation for another class, but not for this class. So they're going to use the notion of production as the basis of the asymmetry, and that'll be also the distinction between causation and correlation. Smoking produces cancer, right? Whereas using an ashtray does not produce cancer. Production is also temporally asymmetric, so exercise produces fatigue, but fatigue does not produce exercise. Now, you may be suspecting, what do we mean by production? Or isn't this just sort of a synonym for cause? Uh, Maybe so, right? They admit in the text, and I will admit here that switching your using the word causation to the word production is not like really a huge leap in understanding much about the metaphysics of causation, but we can leave it there, right, for our own purposes. It won't matter much for what follows. We all understand, I think, what causation is and what production is well enough to evaluate, right, scientific evidence. Okay, so right now we're going to sort of build up some formal stuff. They use a convention, right? In the text, they have like bolded C to stand for a causal variable, and then not bolded C to stand for like the value of that variable. It's a little confusing, and it won't ultimately really matter, right? So I'm not going to like on the exam or any quizzes or anything like try to trick you on like, am I talking about a bolded C or a not bolded C? So don't freak out when this seems confusing. Just try to follow it because it's just for to try to keep things clear for you to understand the concepts, right? So it's not meant to be a way to trick you. Okay, so let's just go through this. This is the sort of the formal our formal account of uh, how we can start to understand uh, finding evidence for causal claims using statistical models. So take an individual in a population, right? So it could be me, it could be a particular rat, right? But it's just one thing. Um, we're going to characterize that individual using a set of variables, right? Um, and values of those variables. Uh, I think I put the question mark here because I was wondering whether it was significant for them that they chose variables instead of the values. It won't matter for our purposes, right? Um, so these might include sort of like, oh, right, because all of these examples they give in the text are actually values of variables, right? So the variables would be color, right? Uh, Smoking status, cancer status, and so on. Um, so again, it's not going to matter for anything important, right? But anyway, so we got an individual, right? So we want to say, what is this individual? For our purposes, an individual is just going to be sort of a set of these variables or values of these variables, right? So just the ones we care about. Um, so among these various variables, so right, for example, right, here's Nate. There's many, but infinite number actually of values of variables you could use to characterize me. Um, right, by my age, right, has a beard, is wearing a black shirt, right, is Caucasian, um, has blonde hair that's going a little gray around the temples, has blue eyes, doesn't smoke, uh, lives in California, right? So on. Infinite number of right values of different variables you could characterize me. Only some of them hopefully will be the ones of particular interest, right? And one of those might be a cause that we're interested in, right? A causal variable, and one of them might be an effect variable that we're interested in, right? So uh, has skin cancer, right? Might be one sort of effect we're interested in, right? And has freckles or has fair skin, right? Might be another. So we might wonder whether having fair skin is a cause of, right, having skin cancer. And I do have the fair skin value of the variable. I don't have the skin cancer value, right? Um, and so on, right? So just think of an individual as a set of, again, values of variables, and you can pick out any two and wonder if one is a cause and one is an effect of that cause. Okay, so they're going to call they're going to use bold, in the text, they use bold C, but it doesn't show up in these slides. So I'm using black C to stand for a causal variable. And then that variable can have possible values C and not C, right? So we might say fairness of skin, right? So it'll be fair and not fair, right? Has skin cancer, it'll be, again, has cancer or does not, right? These binary things, right? And then same with the effect. So the black E stands for the variable of the possible effect, and then the possible values. So has skin cancer, does not. Okay, so the rest of the variables, so certainly I've got more than two variables, right? Values of variables. All the rest of those characterize the residual state. Um, so the black S stands for sort of all the possible residual states. Remember, each one, I could have it or not have it, right? So it's going to be 2 to the n. So n is, right, the list of all the variables besides the causal and the effect variable. So again, for me, having blonde hair graying around the temples, right? That's one of the variables in my residual state. It's not a potential causal or effect variable that we're interested in. Um, me being 5'10", right? These all characterize my residual state. Big, big, long set of them, right? Potentially infinite. And in fact, there's going to be, however many there are, there's going to be 2 to the n because I might have either have that variable value or have the not. So not have blonde hair graying around the temples. So that's what makes it 2 to the n. Does that make sense? Okay. So you look at my residual state, it might look like this. For variable, right, skin, fair or not fair, I have fair, right? So S1 is fair. For variable, right, is African American or not, I'm going to be not, right, and so on, right? Obviously, infinite number of ways you could characterize these variables, right? We're making them binary, right? Um, so I could, if you were thinking about ethnicity, right, you could have different sets. So African American or not, right? Hispanic or not, Asian American or not, and so on, right? Um, okay, is that clear enough, right? So we got this whole set of, again, values of variables that could characterize me, um, and then two of them we're interested in, the cause and the effect. Okay, so using this machinery, right, these sort of stipulations we've made, now we can define the notion of a causal factor, something we're interested in when we're trying to determine whether something's a cause. So C, we can say C is a positive causal factor, and this is in a deterministic model. We're going to talk a bit about more what that means for E. So again, C is a value of a variable, E is a value of a variable, right? So again, having fair skin, right? Is it a causal factor for having skin cancer? And an individual I, call that individual me, characterized by a residual state S. So my residual state, again, is like having blonde hair, blue eyes, and all the other values of variables that I instantiate. So it's a possible, C is a positive causal factor if C produces E and not C produces not E, right? So fair skin would be a cause of skin cancer if having fair skin produces cancer and not having fair skin does not produce cancer. Um, that seems, we'll see later, that seems pretty strong, right? Obviously, not everybody who has fair skin ends up with cancer, right? Just like not everybody that smokes gets cancer. Um, but we're starting with this notion so we can then get subtler notions later, right? So a for sure deterministic thing might be, um, right, if C has his head removed, then E is dies, right? So like in that state, having your head removed, right, produces death, and not having your head removed produces not death. Okay, so C is a negative causal factor, again, a deterministic model for E in an individual I, characterized by that whole set of residual states. If in that individual, the cause produces not E, and not having the cause produces E, right? So there, that makes sense, right? So if cholesterol is a cause of heart attacks, right, then you might also want to see if taking cholesterol medicine is a cause of not having heart attacks, right? So in that case, you want to see if it's a negative causal factor. So does C, right, the cholesterol medicine produce not heart attacks, and does not taking the cholesterol medicine produce heart attacks? Right? So if C is either a positive or negative causal factor for E and I, given the residual state S, we'll say that that variable is causally relevant for E and I. Right? So there's two ways that something can be causally relevant. It can either produce an effect or the produce the absence of an effect. And in either case, it is causally relevant. Now, if it's neither, right? So if having that cause does not produce the effect and not having the cause, right, has no effect. So sorry, I should be more precise there. If having the cause, right, is neither positive or negative, right, it's not doesn't reliably either cause or not cause the effect, then we can say it's causally irrelevant, right? So here we're talking about deterministic. So what we're saying is anytime you got the cause, you got the effect. That would be causally relevant. Anytime you don't have the cause, you don't get the effect. That would be causally relevant. Um, but if it's not that reliable, then in this particular model, deterministic individual causation, we say causally irrelevant. Here, this picture is like of twins, right? And one smokes and one doesn't. So you can kind of see the difference, right? Um, okay, so again, the reason we call this deterministic, I promised more about what we mean by deterministic, that given the residual state S, the presence or absence of the cause, the causal variable, right, the value of that determines the presence or absence of E in the individual. So again, this is much more saying that just both C and E are present in the individual, right? Um, that could be the case. I could have fair skin and I could have skin cancer, but that's not enough to say that the fair skin was the cause, right? Um, there's a lot of other things I have too, and those aren't causal factors, right? All these other things in my residual state. So to say that C is a positive causal factor is to say this sort of like modal claim, or like it's a claim about what would have happened in different circumstances, right? It's saying that if C wasn't present, E wouldn't be present. Um, so I might have fair skin, I might have skin cancer in reality, right? But to say that the fair skin is the cause of the skin cancer is to say that if I hadn't had fair skin, which is a pretty like wild claim, like the world would have to be pretty different, right? I would have had to have different parents and so on. And getting into the metaphysics of that is weird, but like that's the claim, right? If I say my fair skin is a cause of my having skin cancer, I say that's to say that if I hadn't had fair skin, I wouldn't have had skin cancer. So this is obviously much stronger and more interesting claim than just mere correlation, right? Now we're making sort of claims about like other possible ways the world could have gone, right? Um, Now the residual state, very important, right? So if you take two people with the same total state, say for example, these twins, now are they really going to have the exact same total state? Well, no, like one will have a different name and so on, right? But they're as close as we can get in real life. Um, so say the presence of so say we have two individuals, right? Same total state except for one of the variables, right? Um, Now, in that case, right, you might have, it might be that C is a causal factor for one of them, but not for the other, right? Which means that the difference of that one factor, right? So say we had twins, but one of them has a mutation on one gene, right? So they're, well, no, they're genetically identical. Okay, so we have two twins, right? But one of them plays golf and one of them doesn't, right? One of them, uh, right? They both have the same causal factor. Say they both smoke or something, right? One of them gets cancer, one of them doesn't. If there's only one difference in their states on this deterministic model, that must have been the difference. Playing golf must have been the difference. And if so, that would make playing golf causally relevant, right, to the effect. So I tried to use examples, but let's use the actual example they use in the text. So here's a mouse, right? We'll call him Izzy. So we'll see in much more detail. We're going to cover a study that ingesting saccharin is a positive causal factor for bladder cancer in laboratory mice. Right? Now that study uses a whole population of, or a sample of the population of mice, right? It uses more than one mouse. But let's talk about one mouse, Izzy, right? So he's got a set of residual states. Let's say he's male, he's white, he's healthy, etc., right? So if we're trying to claim that saccharin is a positive deterministic causal factor for bladder cancer in this individual Izzy, given his residual state, what we're saying is that if we give Izzy saccharin, he's guaranteed bladder cancer. And if we don't give him saccharin, he's not going to get bladder cancer. So again, on this deterministic model, saccharin makes all the difference as regards bladder cancer in Izzy, right? And again, in all these examples, that seems a little implausible, right? In real life, it seems like there's never just like one factor that makes all the difference, right? But hang on. In a sense, you're right, but let's talk about this in another sense. You kind of assume something like this, I think, in your everyday understanding of the world. So, like, is this possible, right? Doesn't that seem a little simple to say that one factor could make all the difference, right? Given your residual state, it guarantees cancer or it guarantees no cancer, right? Um, well, something like this is in the background of our causal reasoning, right? So again, suppose you got identical twins, and they come down with the same medicine, or sorry, they come down with the same illness, right? And the doctor prescribes the same medicine to both of them, right? But one recovers and one doesn't. Well, how could we explain this, right? You've kind of got two options, right? Um, One is to just say, I don't know, sometimes stuff happens. The world is crazy, right? There's just randomness out there in the world. You can say that, right? But probably what you actually would think in that situation is, well, even though they're twins, there's some difference in the two, right? And there's some reason why one got better and one didn't, right? It wasn't just sort of random, or it didn't just sort of like, well, sometimes just things happen, right? Probably you would explain it by some minor biological or chemical difference in the two, right? And if that feels natural to you, right, to say that, yeah, if there's differences in outcomes, then there's got to be differences in the individuals. Um, that's all that this deterministic model is saying, right? It's saying you're not going to get a difference in the outcome without some difference, right, in either the causal variable or the residual state, right? So again, on the deterministic model, right, the reason maybe that it felt implausible to you um, that bladder cancer, sorry, that saccharin can make all the difference, right? The reason is you need to think through all the details of the residual state. We rarely know all the details for the residual state, but if all that were spelled out and we knew every part of the residual state, then on the deterministic model, we totally could know, right? Um, the Whether a cause would determine the effect or not. So that's what determinism means. It's not saying that we know every bit of the residual state. It's saying if we knew every bit of the residual state, then everything would be deterministic, and we could know that a cause would guarantee an effect. And again, this is sort of the whole reason we do research, there's some implicit assumption of determinism here, right? That's when we research cancer, right? It's because we think it's not just up to chance whether people get cancer or not. We think there's causes of it, right? Okay. Even so, though, like if you have the other instinct, right, that well, again, back to the twins, right? They both have the same illness, get the same medicine, and one gets better and one doesn't. If your instinct was, well, no, actually, I mean, yeah, things are a little random sometimes, right? That's okay too. We have models for that, right? So, what would a probabilistic model, right, of causation as opposed to a deterministic model of cause? So, you're not going to have to use that formula. That's just Bayes' theorem. I was just looking for an image, right? So, but don't worry, you're not going to be using Bayes' theorem. Um, So how does a probabilistic model work? Well, in a probabilistic model, the value of the causal variable, instead of guaranteeing the effect, right, or if it's a negative causal factor, guaranteeing the failure of the effect to obtain, um, it's just going to change the probability of the value of the effect variable. So on a probabilistic model, we'll say C is a positive causal factor, probabilistic, for E in an individual I characterized by a residual state S if in I the probability of E given C is greater than the probability of E given not C. So all it's saying is if you have, right, that value of the causal variable, it increases the probability that you'll have a certain value of the effect variable. It doesn't guarantee it. And likewise, if it's a negative causal factor, right, that means it will decrease the probability of the that value of the effect variable. And if the probability is same in either case, right, whether you've got C or not C, then we'll say that C is causally irrelevant for E. That hopefully seems maybe a little more natural approach to how we talk about these effects, right? So typically we'll see that when we're talking about causation, right, we say smoking increases your chances of cancer, right? It doesn't guarantee lung cancer. Certainly there are people that live long lives, never get cancer, and smoke for a long time. Right? Okay, so this might feel a little strange or new to be talking about probabilities in individuals, because so far, whenever we've talked about probabilities, we've been talking about a population, right? What is the right? When we're talking about the probability of red. Sorry, I'm getting some strange lighting here on this movie. Right, think back to our marbles, right? We said the probability of red in the population of marbles being 0.5, right? We're talking about half the marbles being red, right? Now we're talking about probabilities in an individual, right? Like in a particular marble or a rat or a person, right? Um, so what does that mean for our purposes, right? Um, so there's different ways you can interpret probability, and again, that's getting a little more philosophical than we will get in this course. Um, but you might think about it this way, right? So you can still think of the same person, the same individual, and just think of them being and having the same residual state, right, of all the other, blondness, blue eyesness, or whatever, and just being subjected to see and not see over and over, right, multiple times. Um, if you need to think of it as in like different alternate worlds or whatever, right, that's fine. Or maybe not, right? So if you want to say being hit over the head is a positive causal factor in me losing consciousness, you could try that over and over, right? You could hit me over the head as many times as you like. You could not hit me over the head as many times as you like. Um, and then we've got a sort of a population, right, of these various events, right? And then we can say, okay, the relative frequency of E's when the causal variable has C would then be the probability of E given C, right? So then relative frequency of me getting knocked out when I'm hit over the head, right? That's the probability of E given. Um, so, in reality, in many of these cases, you can't do that, right? Smoking and cancer, you can't sort of give a person another life where they don't smoke. So in those cases, using this understanding of probability for individuals involves sort of a hypothetical scenario where you think, oh, what if they lived their whole life and didn't smoke, right? And what if we imagine that 100 times or something like that? Then we can sort of use our same notion of probability, talk about probabilities for individuals. So it may have occurred to you, right, that there's not really any way um, to know all of the characteristics that make up somebody's residual state, or which ones will be relevant, even if you're not focused on all of them, right? Because I have one of the values of my residual state is I'm more than 100 miles away from the moon, right? I'm more than 101 miles away from the moon. I'm more than 102, more than 102.1, 102.2. So in principle, I have an infinite, right, number of variables that make up my residual state. So how do we deal with that, right? And again, as we saw, like for an individual, uh, whether whether the causal variable guarantees the effect can be affected by one of the variables in a residual state, right? Um, Again, are twins, right? If the cause creates the effect in one but not in the other, we tend to assume, oh, there must be some difference in the residual state. Um, but then what is it, right? How do we know for any individual? Like we can't elaborate the whole residual state. So this is why we typically use populations to figure out to evaluate causal hypotheses, right? So if you study a large group of individuals, then you can kind of figure that their residual states will sort of average out. And effectively, many of the variables will be canceled out, right? So lots of different people with lots of different hair colors, right? Um, we can kind of, in the end, rule out hair color probably as a causal factor, right? If there's differences, right, in the effect, well, it can't be hair color because we have people of all different hair colors. Right? That's the idea. So we can adapt our deterministic model for causation in individuals to populations, and then we'll adapt that model to a probability. All right, attendance quiz time. Oh, the sun. All right, so this is time for you to type this in your browser if this is how you do it. And if it's taking you longer than this, you can pause. All right, moving on. Okay, so a comparative model for causation in populations, right? So really all of these studies are going to be using populations, right? We're never going to try to evaluate a study that only uses one rat. Uh, the reason that we set up our definition of causation in terms of individuals is now we're going to use that notion to define causation in populations. So say you've got a set of n individuals in a population, and let's start with a deterministic model. So we've got a set of, say, 100, right, deterministic individuals. Okay, we'll then say that C is causally relevant for E in a population U. So U is the name of the population. If there are any individuals in U for whom C is causally relevant for E. Um, so that might seem a little strange, right? So wait, so it'll be causally relevant in this whole population of 100 individuals if there's only one, right, for whom it's causally relevant. Yeah, that's what we're saying, right? But that's going to be useful later when we get into it, right? But what we need then is a method for finding out whether there is any individual, right, for whom C is causally relevant, even if we can't necessarily pick that individual out. So what we want to know then is whether there's any individuals in the population, again, for which C produces A. That would be sufficient for causal relevance in a population if only one individual, right, uh, has that relationship between the cause and the effect. So one way to think about that is to say, well, what would happen if every individual in the population exhibited the value C of the variable, right? And in particular, we'd like to know, suppose that all of the 100, right, in our population did have the causal variable. Uh, would any that currently do not have the causal variable and do not have the effect, right, would giving them the cause them to change to having the effect, right? So we've got our set. Um, we've got our population. Some are smokers, some are not smokers, right? So we're asking, if we made them all smoke, right? Would any of the people that now don't have lung cancer, would they get lung cancer, right? Um, if so, then there's at least one individual in the population, right, with that C to E relationship, right? Um, and that would be sufficient for causation in the population. Okay, so in the population U, right, some percentage of the members of the population will have the effect variable, right? Say lung cancer, right? So the probability of E in U is going to be, right, capital P, little u. So that's the probability in U of that effect. So the probability in U of having lung cancer, for example, right? Now, so let's say, I don't know, that like 5%, right, of the population currently has lung cancer. And now what they're saying is, imagine that every member of the population that didn't smoke now smokes, right? Um, and that creates a new population we can call X. So X is the population where everybody smokes. Everybody has the causal variable. So X is just like U, right? Except that every individual member of X exhibits C. Um, so now in X, there's also going to be some percentage of the members that exhibit E, right? So before we said it was 5% in U. And the question is it going to go up in E, right? If you make everybody smoke, is there going to be a higher percentage of lung cancer, right? Um, and all you need is one, right, for that percentage to go up. If the percentage goes up at all, that means at least one person has that causal relationship, right? That they didn't smoke, but if you made them smoke, right, it made them switch from not having cancer to having cancer, right? It changed some not E's to E's. So if there is a causal relationship, we ought to expect that the probability of the effect in the population where everybody has the causal variable should be greater than the probability of the effect in the population where there's the mix, like some smokers, some non-smokers, right? Now let's imagine another manipulation to our population U, right? Let's suppose that we changed all the C's to not C's so that now all of a sudden all the smokers are non-smokers, right? Um, so again, if there's a positive causal relation between C and E, then you should expect fewer cases of cancer in the new population where no one smokes, right? Um, so now we can put these two sort of hypotheticals together, right? And we can say if there are any individuals in U for which C is a positive causal factor for E, right? Um, whether or not those individuals happen to exhibit C or C and E or not C and not E in U, um, it should be the case that the probability of E in population X, right, that one where everybody has a causal variable, will be greater than the probability of the effect in K where no one has a causal variable, right? So we're taking a normal population, we got a mix of C's and E's, and we're saying, let's imagine that we sort of make them all smoke, right? See if the effect goes up. Make them all not smoke, see if the effect goes down, right? So if in those sort of two imaginary worlds where all of them smoke and all of them don't smoke, if there's a greater probability of the effect in the all smoking, then we've got a causal relationship. So C is a positive causal factor for E in the population U whenever PXE is greater than PKE. Again, X is the one where everybody has a causal factor. K is where nobody does. And C is a negative causal factor. So again, this is the reverse. if PXE is less than PKE. So that's the situation where maybe, right, we have a population, some of them have high cholesterol, some of them have heart disease. We take one group, we give them all cholesterol medication. We take another group, none of them get cholesterol medication, and you want to see less heart disease in the group where they get cholesterol medication. Um, and then if the two are equal, right, it's a probability it does not change. So in the population where everybody smokes, the probability of cancer is exactly the same as the population where nobody smokes, then we would say that it's causally irrelevant, right? Now, notice maybe you're thinking of this. Well, that seems to entail that C could be causally irrelevant for E, even when it actually is causally relevant for some individuals, right? So, like, if you've got um, in PX, right, someone did flip to having E, right? Or oh, it makes more sense if I say so. In PX, right, somebody flipped to not having E, and then in PK, somebody flipped to having E, right? So uh, in one, it was a negative causal factor, another, it was a positive causal factor. Um, but nonetheless, right, those two would sort of cancel each other out. The point being, that was maybe a little confusing, but the point being, you can see how individuals could sort of cancel each other out, right? And you'd still have like no difference in the probabilities, right? The uh, in the relative frequency, right, of E's or in the population. Um, so there is sort of an in principle gap here between our model and reality, but uh, in that we're claiming there is a causal fact. If for any individual it is a causal factor, right? That so we're just saying if there's even one person, right, then we use that to define being a causal effect in a population. But then we turn around and say, well, using this method, of course, it could be the case that there are two individuals for whom it is a causal factor, but it's exactly opposite, and so they cancel each other out as far as our calculation. That seems a little confusing, maybe potentially contradictory, um, but it's so unlikely that that would ever happen in reality that we can use. Okay, so again, that's the model for causation in populations, right? For deterministic individuals. So what if the individuals are probabilistic? Basically, same idea, right? The only difference is that these probabilities are no longer now just the number of individuals in the population that have it, right? So you can't just look and say, okay, what's the probability of E? Well, how many people have cancer? Um, Now it's going to average, because remember, on a probabilistic view, having the causal variable um, affects the probability of having the effect variable. So now, for any individual, it's a causal factor if it changes the probability. So now, in calculating PXE and PKE, you're taking the average of the probabilities for each individual, right? Um, but in the end, um, that average, if it differs in PXE and PKE, we see a causal, and there is a causal relevance, right? So the evaluation is going to be similar, right, in either case. Okay, getting towards the end of, again, this is all the conceptual stuff, and then in the next two lectures, we're going to talk about how to actually sort of make the evaluations, types of studies you might use. So this is all just building up like a definition of what it means uh, to have for something to be causally relevant. Um, but another concept you might be curious about is the effectiveness, right? So sometimes things can be more or less effective, right, causally. Um, we do this all the time, right, when we're thinking about like approving a drug, right? So uh, typically we don't go through the trouble of manufacturing a drug if we think, well, I think there's one person out there we could potentially help, right? Usually we want it to be sort of effective broadly, and we want a relatively large increase in quality of life and so on, right? So that notion of like how much of an effect does the cause have? That's what we call the effectiveness of a causal factor. So on the deterministic model for individuals, there's really only three grades of effectiveness, right? Is it a positive causal factor? Is it a negative causal factor? Or is it irrelevant? But when we're moving to the probabilistic models, now we can sort of like say a lot more, right? We might want to know how much does it increase the probability of the effect, right? And that's a measure of effectiveness in a more interesting way. So the probability that a cause will bring out an effect in an individual, of course, ranges from 0 to 1. 0 meaning that it's not going to produce any effect. 1 meaning every single time it's going to produce the effect. And then 0.5 means half the time it'll produce the effect. So the effectiveness of C in producing E, so we'll call that capital E, little f means effectiveness, and then C, comma E. So the effectiveness of C for producing E, that's just going to be the difference between the probabilities of the probability of E given C and the probability of E given not C, right? So we have our little calculation there. So the maximum value there will be a 1, the minimum value will be a -1, and then 0 will indicate causal irrelevance, right? So that's 1 is guaranteed sort of positive causal factor, -1 guaranteed negative causal factor, and if it's right in the middle, that's causal irrelevance. And we can also talk about effectiveness in populations. So for a population model, assuming a deterministic model for individuals, we can measure the effectiveness of a causal factor in the population. That'll be the difference between those two probabilities that we already talked about, right? The probability of X, probability of E in X, right? Which is again the world where we take all our people in our population U and we give them all the causal factor. If you subtract that the probability of E in the population where nobody has a causal factor, that's going to be the effectiveness. Again, it can range from -1 to +1, right? And 0 effectiveness means causal irrelevance, right? +1 means guaranteed positive causal factor, -1 guaranteed negative. And so that's on the deterministic model. Now, if we're thinking about the probabilistic model, same calculation, right? But now PXE uh, is the average, right? So it's the expected value, right, which is basically the mean, right, of the probabilities in that population. So again, each individual has a certain probability of the effect, right, and then we average all those probabilities, and that's what we use for PXE or PKE in a probabilistic uh, population model. Okay, so summing up here, um, again, this is when we actually get into this, right? They're all going to be studies using a population, right? And we're basically going to be using roughly the same correlations over and over, or sorry, same calculations, right? Uh, so all of this lecture was building up, in principle, the machinery that shows why this is a rigorous method, right, for finding causation. Um, so you need to understand this stuff. Like it will be on the exam, but then when you get into actually sort of doing the math and evaluating this stuff, um, the stuff from this lecture is not going to like come up over and over and over. So let's apply our models. The example of smoking and lung cancer. So there is a positive correlation between smoking and lung cancer. We can assume this, right? So all that means is there's more cases of lung cancer among smokers than there are among non-smokers. But the question is there a causal relationship, right? Is smoking a positive causal factor for lung cancer, or is it just a correlation and something else is the cause? Okay, so here we're going to define correlation uh, as relationships between the properties in an actual population, right? Uh, we know that there is a larger percentage of cases of lung cancer among smokers than among non-smokers. And then whether it's a causal factor, right, is to say that there's a relationship between two hypothetical versions of the real population, right? So to say that smoking is a positive causal factor for lung cancer is to say that there is in fact, wait, oh, sorry, it's to say, yeah, say more than the fact that they're, so again, the correlation just says, yeah, there's more lung cancer in smokers than there is in not. Um, to say there's a causation is to say much more than that, right? Is to say, if everyone smoked, there would be more cases of lung cancer, right? If no one smoked, there would be no cases or fewer cases if it's a probabilistic model of lung cancer, right? Um, so this is the essential difference between causal claims and correlations, right? Is making these sort of modal claims that's saying it's not only the case, right, that we see a larger proportion of this value of a variable in people that also have this value of this other variable. It's saying, um, take these two variables, let's go to a world where everybody has it, right? Let's go to a world where everybody doesn't have it. You're going to see a big change in the effect variable as well. Okay, so I hope that was helpful. Again, this is all the sort of machinery, sort of the fundamental definitions and stuff, building up this account of this rigorous account of what it means to be a causal variable, right, to have a causal relation between two variables. And so next, we're going to start to see how to take an actual study. The first will be randomized experimental trials. So the different kinds of studies you can do, right, to evaluate a causal hypothesis are in sort of like decreasing uh, amounts of like how good we think they are as like methods, right? So that we'll start with the gold standard, which is like a randomized experimental trial where you get in there and you actually take a group of rats, right? And you actually sort of create these populations, the population X and the population K, right? And one of them, you give them all saccharin, right? And the other one, you give them no saccharin. And then you see uh, then whether the probability of the effect or the relative frequency of the effect goes up or not, right? So it's as close as you can get to instantiating this sort of these hypothetical other worlds, right, that we're talking about for the causal variable. And then the other versions, they try to approximate it in sort of less uh, okay, I guess where are we? Oh, we're at 15 minutes. So that's good for today. And yeah, oh, again, if you're not keeping up or if this gets confusing, it's hard in this remote format sometimes. So do sort of like in discussion, bring stuff up. No one's been coming to my office hours. Please come. Like I'm just hanging out, right? So I'm happy to talk to any of you if you're starting to feel confused. So um, we have to make use of this stuff more when we're not in a lecture hall together. So I hope you're keeping up, and I'm happy to talk to any of you that are not.